Yeah, you can now you can continue.
Okay. So in this class, we are going to see about soil water, one of the most important topic in soil science. You can expect more questions in soil water in your exam. So coming to its definition and meaning, soil water. So what is soil water? Soil water is the water held by the soil particles against forces which try to remove them. So water, whenever it is present in soil, it is present. It is having some force. Force in the sense it is held with some energy. So plant has to spend that energy. Then only it can extract water from the soil. So water is held in soil with some energy. So the plant has to spend that particular energy so that it can able to extract or absorb water from the soil. The energy is low, the plant can easily extract water from the soil. If the water in the soil is held with more energy, the plant has to spend more energy to extract water from the soil. So that this is the basic concept on plant absorbing water from the soil. And it is important to understand that all the water present in the soil is available for crop uptake. Again, you need to know that there are a lot of water present in the soil, but all the water are not available for the plants. If I say plant available water, it is only minus 3 bar to minus 15 bar only. If it goes beyond minus 15 bar, it is not available to the plants. And it is also, if it goes less than minus 3 bars also, it is not available to the plants. We are going in further slides, we are going to see some soil moisture constant terminologies. If you go through that, you can clearly understand what is available to the plant and what is not available to the plant as far as soil water is concerned. Then it is also the fact that the water contained in the soil is not chemically water. So water as such, it is present, it is water. But water in soil, it is not chemically water. Chemically, we can call it as a solution because it contains some dissolved nutrients also. So water we can't call the water that is present in the soil is water. Otherwise, we can call it as a solution. So these things we need to know before entering into the topic. Then coming to the occurrence and chemistry of water molecule. If we take water molecule, its molecular formula is H2O. That means it contains two hydrogen and one oxygen atom. So if you take the diameter of the oxygen, it is 2.64 Armstrong. And this hydrogen molecule is attached to the oxygen at 105 degree. In some books, they given us 103 to 106. On an average, if we take, it is 105 degree. So this hydrogen atoms contain net positive charge and this oxygen atom contains net negative charge. So water is a dipole in nature. Dipole means it carries both positive and negative charges. So water molecules are bonded with each other very tightly. This water molecule tend to bond with each other very tightly. Then, if we are going for irrigation, we are applying water to the soil. How come the soil is absorbing or retaining water in it? So water is retained in the soil in micropores as well as macropores. So how it is retaining? It is mainly due to this three forces. One is your cohesive and adhesive forces. What is this cohesive and adhesive? Cohesive means it is forces that has been happening between similar molecules, attraction between similar molecules like liquid or solid. What is this adhesive? Force of attraction between dissimilar molecules. It may be due to solid liquid. So this is cohesive and adhesive. Because of that, water is retained with the soil particles and also due to surface tension. It is mainly between the cohesive nature of the liquid molecules. This surface tension has been happening. And the third one is polarity dipole character. As we discussed earlier, water is having both positive and negative charges. So the soil is having negative charge. So the water can be attracted, water can be absorbed by the soil. Water can be. So because of this three nature, water is being retained in the soil. Then how we are going to express the soil water that has been present in the soil. So we can express in two ways. One is the pF scale. Another one is your atmosphere or bars. What is this pF scale? If you know about pH, what is the pH? It is a negative logarithm of hydrogen ion concentration. What is this pF? It is negative logarithm of height of water column. It denotes the height of water column and it also denotes the pressure that has been required to absorb water. Suppose if you're having a wet soil and dry soil, in wet soil, if you take the pF value will be 0. That means the plant will not spend any energy to absorb water from the wet soil. if we go for a dry soil, the pF value is 7. That means the plant has to extract more, spend more energy, then only it can absorb water from the soil. And the second one is your atmospheric bars. It is just measuring the average air pressure at the sea level. How much pressure that has been water, how much pressure that water has been held in the soil. It is just measuring the pressure of the water. Then coming to the conversion, atmosphere or bars, 1 bar is equal to 1020 centimeter of water column. This is just conversion unit. And if you take the SI unit of pressure, nowadays they are calling it as in kilopascal. So 1 bar is equal to the 100 kilopascal. We can see some examples. If we take the water is in 1000 centimeter of water column, then we can call it as 1 bar, because 1 bar is equal to 1020. So 1000 centimeter of water column is approximately 1 bar. And then 1 bar is equal to 100 kilopascal. So we can multiply by 100. Whatever the bar is coming, we need to multiply by 100. If it comes 1 bar, it is 100 kilopascal. If it comes 10 bar, it is 1000 kilopascal. So these are some of the conversion units, because in exams they may ask in kilopascal sometimes. Then we can convert to bars. Then they will give the option in bars. Sometimes they can ask in bars and they will give the option in kilopascal. So you need to know the conversion unit. Then you can answer this question. So 1 bar is equal to 1020 centimeter of water column. So, and then 1 bar in another way, you can also put it as 100 kilopascal. It is multiplying by 100, it is just multiplying by 1000 in terms of water column, in terms of kilopascal. That's all. Then we are going to enter into the important aspect of soil water, that is soil moisture constants. What is this soil moisture constants? It is mainly used to denote the status of soil water, because water is held in the soil at different pressures. So if we denote, if at particular pressure water, if it is held at -3 bar, we can call it as field capacity. That terminology is known as soil moisture constant. It is used to denote the water that has been held in different pressure in the soil. We will see one by one. First one is your saturation point, or otherwise you can call it as zero tension water or free water. That means water is held with zero tension. Zero tension is nothing but zero pressure. Water is held with no pressure. So when will this event will occur? When will this saturation point will occur? So after rainfall or irrigation, suppose an rainfall event is happening, the water enters the soil pores. If you take soil, there are two pores. One is a macro pores, another one is a micro pores. This micro pores are larger pores. Micro pores is a smaller pores. So water will first enter into the macro pores. So just remember, after a rainfall event, when water is entering into the soil, we will have two pores. One is your macro pores, another one is your micro pores. So water will first enter into your macro pores. Once this macro pores are filled, then the micro pores will be starting filled up. Once the macro pores and micro pores are completely filled, then we can call the state as saturation point. So the plant will not spend any energy. At this state, the plant will not spend any energy to extract water from the soil. The water is freely available to the plant. The water is held with zero tension or zero pressure. Hence, we are calling it as zero tension water or free water. And it is also the maximum water holding capacity. At this stage, we can call it as maximum water holding capacity. So you need to remember three things: the saturation point, the water is held at zero tension, that is 0 bars. It is also a free water. It is a state at which there will be maximum water holding capacity for a particular plant. Okay. Then the second one is your gravitational water. When this state will be happening? So after saturation, as we seen earlier, the macro pores and micro pores are completely filled. Then the macro pores water will be starting to drain out. This water, it is mainly happening due to gravity. Because of gravitational force, whatever the water present in your macro pores are going to drain out. This water will be mainly used for your recharge of groundwater. This water will percolate and recharge your groundwater. As far as soil is concerned, we are having micro pores and macro pores. Once the water has been lost from the macro pores only, then we can have some exchange of gases. If there is exchange of gases only, the plant can respire. So the water has to be lost from the macro pores. Otherwise, the plant can't respire. So what we can call this gravitational water is water in excess of field capacity. Is termed as gravitational water. And this gravitational water is of no use to the plants because it is occupying larger pores. and it is mainly reducing the aeration. Plant require aeration, then only it can grow. It can grow well. Plant also requires some air, as we already seen in the previous classes. Aeration is required for the optimum growth of the plant. So it requires some aeration. For plant to have some good aeration, it should lose its gravitational water. So thus its removal from soil is a prerequisite for optimum plant growth. So what pressure it is held? If you take the gravitational water, it will be held at the pressure of 0 or less than 1/3 atmosphere. Then we can give it as a gravitational water. So this gravitational water is nothing but the water that has been lost from the macropores due to the force of gravity. It is called as your gravitational water. If you measure the pressure of this water, it is 0 or less than 1/3 atmosphere. Then the third one, it is your field capacity. It is very important. At this state, only the plant can absorb more water from the soil. After the equilibration of soil water with the force of gravity, that means the gravitational water has been lost, the macropores being depleted, the water is held with an energy status which is equal or greater than the force of gravity. The state of water is called as field capacity. The water in the soil is held at the tension of 1/3 bars, minus 1/3 bars. Then we can call it as a field capacity. Field capacity is nothing but upper limit of water holding capacity, available water holding capacity. Earlier we have seen that saturation point is the maximum water holding capacity. Now this field capacity is upper limit of available water holding capacity. Here the water is at the tension of nearly minus 1/3 bars. Then allowable depletion point or refill point. So the thickness of water molecule is still reduced because at saturation we are having more water. At gravitation we have reduced. At field capacity again we are reducing. So the thickness of water is reducing. So water molecules are retained with more suction. So water molecules tend to have water molecule soil retained with more pressure. So plant has to extract the same amount of pressure. Then only it can extract the water from the soil. After a certain point of state of soil moisture, the plants have to extract more energy, which may result in reduction in the yield due to energy spent on absorption. So the plant, when the plant is at saturation, when the soil is at saturation point, plant needs only less amount of energy to extract water. At the same time, the plant is under, if it is goes beyond field capacity, the plant has to exert some higher amount of energy. So it may result in yield loss to the plant. A state at which the plants can take up water at ease without significant reduction in yield is called as your refill point or allowable depletion point. This allowable depletion point is meaning is that at this particular state we cannot go for irrigation. If we are having a soil and if we are irrigating that up to this point, we can somehow manage. If it goes beyond this point, we need to definitely irrigate our field. Then only the plant can absorb water. That is the meaning of this allowable depletion point or refill point. A state at which a plant can take up moisture at ease may be varying between the plant species. It depends upon the plant species and also your environmental condition. It varies. Then the temporary wilting point, as the word itself denotes, it's temporary wilting. If it goes beyond field capacity, the plants may show signs of symptom due to water deficiency. If we are giving water, the plant can recover from that symptom. That is called as your temporary wilting point. The plant will begin to show some symptoms, and if we are giving water, the plant will recover from that symptom. It is called as your temporary wilting point. Then what is this permanent wilting point? The plant will show severe signs of symptom. Even if we are giving water, the plant may not come back or may not be revived because it will show permanent symptoms, permanent wilting point. So water will be held at a tension of around minus 15 bars. The water is at minus 15 bars tension. The plant will be in the state of permanent wilting point. Even if we supply water, the plant cannot be revived back. It will result in death of the plants. So the permanent wilting point is otherwise called as the lower limit of water holding capacity. So earlier we see the field capacity is upper limit of water holding capacity, that is your minus 3 bars, and this permanent wilting one, that is your minus 15 bars, it is your lower limit of water holding capacity. So whatever the water that is available between this minus 3 bar to minus 15 bar, that is called as your plant available water. So that's one, that is your hygroscopic water. What is this hygroscopic water? The water that held tightly on the surface of soil colloidal particle. This water, there is one terminology called soil colloids. We will discuss in detail whenever when we are entering into the soil chemistry topic. It is that the soil colloids, in the sense, the particle having size range of less than 0.0002 mm, then we can call it as soil colloids. And it is essentially non-liquid. Here the water will be presenting in a vapor form. It is not. It is not. It is not. It is not present in a liquid form. So this hygroscopic water is held at a pressure of nearly minus 31 to 10,000 atmosphere bars. So it is not used by the plants. It is used by certain microorganism only. So it is also one of the soil moisture constant terminology, but it is not helpful for the plants. You're just knowing that hygroscopic water. Whenever I say hygroscopic water, it is between minus 31 to minus 10,000 bars. Just remember that. That is enough. Then, as I mentioned, the available water holding capacity, that is between field capacity to permanent wilting point, that is 1/3 to 15 bars. Hence, the water that is available above field capacity and below permanent wilting points are not plant available. That is, whatever the water that is below minus 1/3 and that is above 15, that will not be available to the plant. Further depletion in soil water by the forces of evaporation results in reduction of water and reaching a hygroscopic water content. Hygroscopic water content, the pressure of the water that is present in the soil will be 31 bars. And then further reduction, again, if it is further reducing due to evaporation, it will become chemical water. At that state, if you measure the pressure at which the water held in the soil, it will be 10,000 bars. So the amount of water that the soil contains at each of these equilibrium points is known as your soil moisture constants. So this is to summarize what we have discussed. If you are having a wet soil, it is maybe due to either your rainfall or if you are irrigating, the water will first enter into a state of saturation. At this state, the plant has to spend only less energy to extract water from the soil. The water that is present in the soil will be having zero tension or zero pressure, so the plants can be easily absorb those water. Then the gravitational force will be acting on it. After the rainfall event is over, the water that is present in the macropore will be started draining out to recharge mainly the groundwater. That is deep percolation. Percolation means that is downward movement of water. It is mainly to recharge your groundwater. Then water has been drained from the macropore, so there will be exchange of gases as well as air. So the plant will receive sufficient aeration, and then it is moving to field capacity. At this point, the plant will have a pressure of around water in the soil will have a pressure of around minus 3 bars. So it is known as the upper limit of water holding capacity. And we are having wilting point. We are having temporary as well as permanent. In temporary wilting point, if we supply water, the plant can able to overcome. If it goes above the temporary wilting point, it will lead to permanent wilting point. Even though if we supply water, the plant cannot be revived. So whatever the water that is present between field capacity to permanent wilting point, that is between minus 3 bar to minus 15 bar, it is your plant available water that will be available to your plants. Then if it goes beyond wilting point, that is to minus 31 bars, that is your hygroscopic water. This hygroscopic water is of no use to the plants because it is in vapor form. It only used by the microorganism, or it can be evaporated to the atmosphere. Then it goes beyond hygroscopic water. This goes beyond minus 31 bar. Then it is called your chemical water. That is minus 10,000 bars. So these are some of the different soil moisture constant terminologies. So here we are missing the refill point or allowable depletion point. It will be in between this. So at that state, we need to go for irrigation of the soil. So this is in short about the soil moisture constant. Then soil moisture constant it is given in two units here. One is your tension, another is your PF. We can go from the bottom. That is your maximum water holding capacity. That is your saturation point. It is almost zero. You can see here tension. PF value is nothing. PF value is also zero. It is almost zero here. And if we go for field capacity, if you see, the tension is around 1/3 bar. And your PF value, it is 2.54 at this case. That is the height of water column. And if it goes to field wilting point, you can see here, it is 15 bars and its PF value is 4.20. And for your hygroscopic water, that is your chemical water, it is 31 to 10,000. And the PF value will be 4.5 to 7. So this table is very important. You can expect some questions in your exams. And whenever we are going to denote the water in terms of bars, we need to denote minus here because it always we will in atmosphere we need, whenever we are denoting the water in terms of atmosphere or bars, we need to give a negative sign. And if we consider -1/3 and -15, -1/3 is higher than -15. Just remember that, because you may confuse, because here it is 1/3, here it is 15. 1/3 is 15 is higher than 1/3. It is not like that. It is because of the negative sign. This 1/3 is greater than that -15. Sometimes they will give this minus negative symbol, and sometimes they may not give this negative symbol. Usually the bars or atmosphere is mainly denoted by your negative symbol. Just remember that. Then we are entering into the next topic, that is soil water potential. If we have in previous class, I told on terminology known as the soil plant atmospheric continuum. While dealing with the soil temperature and soil color, I mentioned this soil plant atmospheric continuum. So whenever a plant need to absorb from the water from the soil, there must be loss of water from the plant. Then only it can absorb water from the soil. The water, the water is moving from soil to root, then root to plant, then plant to atmosphere. So whenever the water is moving from soil to root, it is having some energy, then only it is moving. Then whenever it is moving to root to plant, it also exerts some energy, then only the water is moving. So these are all energy concepts. Whenever there is a movement, there is some force. The force or energy is involved. So the retention and movement of water in soils, uptake and translocation in plants, it's all related to energy phenomena. The more strongly water is held in the soil, the greater is the energy required. So suppose if water is held with more energy in the soil, we need to spend that amount of energy, then only we can extract that water from the soil. In other words, if water is to be removed from a moist soil, work has to be done against the adsorptive forces, because water is held with some coercive and adhesive forces. We need to extract some energies, then only we can absorb water from the soil. Conversely, when water is absorbed from the soil, a negative amount of work need to be done. So the movement is from a zone where a free energy of water is high to one where a free energy is low. Generally, water will move from higher concentration to lower concentration. If the soil is having higher water than your root, then the water will move from soil to root. And similarly, if the root is having higher water than your plant, then only the water will move from root to plant. Then the plant is higher water than your atmosphere, then only the plant can evaporate your water to the atmosphere. So these are all energy driven concepts. So whenever a movement is happening in the soil system or in a plant system, it's all there is an heat or energy is required. So we are entering into the water potential topic. It is just measuring the energy status of water. So water potential will tells you how much energy will be released when a water is moving. The water will have some positive sign. Whenever water is coming down from a hill or a falls, the water will tend to have a positive potential. And water potential tells you how much energy will have to exert to move the water. And whenever the water is absorbed by the plants, that means a negative amount of work is to be done against the adsorptive forces. So it will have some negative potential. So in our case, this is the reason why we are having negative potential, because we are absorbing water against some adsorptive forces like your coercive and adhesive forces. So a negative amount of work need to be done. Then only we can able to absorb the water. So negative sign is there. And then water potential is free water. Suppose water in a reservoir or in a pool, we can that will serve as your zero tension water or free water. So this will serve as your reference level. Whenever we are going to coin the term water potential, this will serve as your reference level. So water will always flows from higher potential to lower potential. So this is your total water potential. This total water potential will depend upon your metric potential, your gravitational potential, your pressure, your overburden, and osmotic. This denotes your metric potential. This is your gravitational. This is your pressure, and this is your overburden, and this is your osmotic. We will deal by one. First one is the gravitational potential. What is this gravitational potential? As I already mentioned, because of that gravitational force, some water has been lost in macropores. So because of gravity, some water is lost. Whatever the water that has been lost to gravity, it is known as your gravitational potential. It is mainly due to the force of the gravity. It depends on the location of water molecules on the surface of the earth. And it is generally measured outside the system. It may be positive or negative or zero. It entirely depends on the location of water molecules. And coming to the metric potential, it is mainly due to the adsorptive forces. What is this adsorptive forces? It is mainly due to cohesive and adhesive forces. Because of that, the soil water has been absorbed. This metric potential are operative only under unsaturated condition. Because under saturated condition, we have our micropores and macropores are completely filled. At that state, the gravitational potential is only active. Once the macropores are drained out because of gravity, then the metric potential will be active. That is will be under unsaturated condition. Remember, students, plants only take water under unsaturated conditions only. Because under unsaturated condition, plants can absorb water from the soil. It can also exchange some of the gases. This condition is favorable for the optimum growth of the plants. The forces include hydrogen bonding, dipole effect, van der Waals force, surface tension forces. These are some of the forces that has been mainly due to your matrix potential, and it is measured within the system, whereas your gravitational potential is measured outside the system. Since the soil moisture condition is mostly unsaturated, the metric potential will always be negative. In the previous case, it may be positive or negative or zero. It all depends on your where we are measuring, where the water is present. And in your metric potential, it is always negative. Then the third one is your osmotic potential. It is mainly due to the presence of some salts. If the water is having some salts, and this osmotic potential may be active, and it is also negative because it is not purer than your pure water. Pure water contain no salts, but your the water is having salts, so it definitely will have lesser value than your pure water. So it is generally negative. As I say, osmosis. What is this osmosis? Water will move from higher concentration to lower concentration through a semi-permeable membrane. So the semi-permeable membrane is the route. It does not permit all the salts to pass through. It has some exception. It may exclude some of the salts in the soil solution. So and in if you take a water will move from higher concentration to lower concentration. Suppose if the water is having some salt, higher salt, then the salt will move from lower salt concentration to areas of higher salt concentration. So water, if it present as such, water potential will be from higher concentration to lower concentration. If suppose the water is containing more salt, then the water will move from lower salt concentration to areas of high salt concentration. So these are some of the basic things you need to know. Then what is this pressure and overburden potential? This pressure potential is mainly arising due to the difference in the pressure between the atmosphere. Sometimes we will have some difference in pressure between the atmosphere and as well as also the plant. So then only the gases can evaporate. The plant, it's depend on the plant whether it is going to absorb or evaporate. It all depends on the pressure difference between the atmosphere and also the microclimate that has been prevailing between the plant. So that potential is known as your pressure potential. And what is this overburden potential? Water is held in the soil, and some amount of soil is above the water. So it will have some mechanical pressure. It is mainly because the water is held on the soil matrix. So soil will have some weight. The soil weight also decides the movement of water. So the overburden potential is due to the mechanical pressure exerted by the unsupported soil matrix on the soil water. And this overburden potential is significant only in swelling type of soils. Swelling type of soil is nothing but the soil that is having more clay, 2:1 clay matrix. 2:1 expanding clay matrix. It will expand, it will swell and shrink. Swell means it will expand and then it will shrink. So it is more in swelling type of soils, because soil, if it is expanding, it is having some overweight, then it is started to shrink. So it becomes insignificant in other soils. Then coming to the movement of water in soils, we take some there are the three definitions: saturated, unsaturated, vapor flow. What is this saturated flow? The water is having the pressure of around -1/3 bars or more than -1/3 bars. The water will be under saturated flow. the dominant force will only be the gravity. If you take the soil moisture constant, that saturation point, we already seen that the micropores and macropores are completely filled with water. At that moment, the gravity is the only dominant force that will be going to act on it. So whenever the water is present more than -1/3 bar, if we take -1/3, it will be coming around 0.33. So as I already mentioned, 1 bar is equal to 100 kilopascal. So minus 0.33 into 100, it will be coming around -33. So it is measuring in kilopascal as well as pascal bar. So if it is more than -1/3 bar, then we can call it a saturated flow. Under saturated flow, the dominant force will be your gravitational potential. Then if it is less than -1/3 bar, that means it is going to wilting point. That means it is going to 2, 3, -2, -3, -4, like that. The flow of water this condition will be expected to occur whenever there is loss of gravitational water from the macro pores. That means all the pores are not filled with water. That means your macropores and micropores are not completely filled with water. Under such condition, the driving force will be your metric potential or osmotic potential. So remember, students, under saturated flow, gravitation potential will be the dominant force acting on it. Under unsaturated flow, it may be your metric or osmotic or some other potential will be acting on it. Then vapor flow, if it is goes less than -15 bar, that is, it is going to hygroscopic or chemical water, then water will be in a vapor form. It will be moves only in vapor form. That this is your three terminologies: water water moving in a saturated flow, water moving in an unsaturated flow, water moving in a vapor flow. Then what some of the terminologies are being involved. Suppose we are applying some water. Suppose we are irrigating a field. Based on the movement of water, we are coining out some terminologies. You will see one by one. First one is your hydraulic conductivity. As I already mentioned in one of the previous classes, we have seen about the definition of thermal conductivity. It is ease with which it is allowing. It is thermal conductivity. It is how the system is allowing heat to pass through. If it is hydraulic conductivity, means it is how easy the system will allow water to pass through. System is soil in this case. It is the ability of the soil to transmit water on the soil. It is generally the vertical movement. Vertical movement, we can call it as an hydraulic conductivity. Vertical movement of water, we are calling it as hydraulic conductivity. Since the movement has to happen to the soil pores, it is directly related to the characteristics of soil pores, like size of the pores and continuity of the pores. So whenever we are seeing water movement, it is happening mainly through your micropores and macropores. So it naturally depends on the size of the pores. When size of the pores is larger, the water can move faster. That is the concept. And there are two terminologies: saturated hydraulic conductivity, unsaturated hydraulic conductivity. Under saturated condition, the gravitational force will be the dominant one. So the movement of water by gravitational force is nothing but your saturated hydraulic conductivity. And your movement of water by metric or osmotic potential, then we can call it as unsaturated hydraulic conductivity. Under saturation, water will move only through gravity, that also only through vertical movement. But under unsaturated condition, either water can move upwards, water can move downwards, water can also move lateral direction. So water is moving upwards, it is under unsaturated condition. Mark my words, under unsaturated condition, and the water is moving upwards, it is mainly due to capillary water. Under unsaturated condition, when the water is moving in lateral direction, it is mainly due to seepage. So seepage is nothing but lateral movement of water. So vertical movement of water is your hydraulic conductivity. Vertical movement of water due to gravitational force is your saturated hydraulic conductivity. So lateral movement of water is nothing but your seepage. Okay. Then what is this infiltration? So here we need to forget the direction of entry of water. Just entry of water, whatever the water is entering, irrespective of direction, whether it is lateral or upward or downward, that is not the case. Just entry of water or movement of water in the soil surface, we can call it as infiltration. The movement may be either upward or downward or vertical or lateral. We need to forget the direction of the movement. It is just entry of water into the soil. Then we can call it as infiltration. Then what is this percolation? It is movement of water through a column of soil. It is also a vertical movement, but it is mainly, the percolation is mainly concerned to recharge your groundwater. Here also the gravitational force will be acting on it. So the vertical movement mostly dominated by a gravitational force. So it is mainly to recharge your groundwater. This percolation need to happen. Then only your groundwater can be recharged, or your macro pores can be left without water, and also your exchange of gases will take place. So percolation is nothing but the movement of water through a column of soil. It is because it is traveling to the ground. So it is that's why they are mentioning it as a column of soil, or else it is a vertical movement of water to recharge groundwater. We can call like that. And permeability. What is this permeability? It denotes the movement of fluids. So earlier case we have seen water. It denotes the movement of fluids means your air or gases. So this infiltration, percolation are all considered the movement of water. But this permeability is mainly considered the movement of fluids, either air or gases, or also water in some vapor form. It also capable of moving. So it denotes the movement of fluids. It indicates the relative ease of movement of water within the soil. The characteristics that determine how fast and air and water move through the soil are known as permeability. Then capillary movement. As I already mentioned, under unsaturated condition, the water is moving against the gravity. That is, water is moving against upward direction. We can call it as a capillary movement. This movement occurs mainly due to the potential developed by surface tension. That is mainly due to the cohesive nature of the liquid molecules. Then we are going to enter into another topic, that is your soil consistence. What is this soil consistence? Suppose we are having a soil and we are applying irrigation. Sometimes we will apply more irrigation to the soil, and sometimes we will apply less irrigation to the soil. So how the soil is going to respond to the various moisture conditions? Suppose we are applying more irrigation to the soil will remain wet and sticky together. Some suppose we are applying only less irrigation, the soil may have some immediately it will be drained out, and we can see some cracks, or we can see some sand nature on this sandy nature. So how the soil is going to respond to various moisture contents? Otherwise, how the soil is going to respond to various mechanical stresses? How it is going to resist to various condition of moisture? That one is called as your soil consistency. Again, the forces responsible for soil consistency is your cohesion and adhesion. As I already mentioned, cohesion means it is attraction between the like molecules that is holding together. It may be between solid to solid or liquid to liquid. And second one is your adhesion. It is mainly due to the molecular attraction that holds surface of two substances. It may be between different one. It may be between liquid to solid or solid to liquid. It depends. So it combines both the cohesive and adhesive forces, which determine if the soil can be reshaped or ruptured. There are different forms of consistency. First one is your dry soil. If you take a dry soil, that means it is having some less water only. So it is having hard or harsh consistency. Soil particles do not stick together. If you take a dry soil, it may not be stick together. It is easily friable. Soil consistency in dry soil depends on the amount of surface contact. That means if you take a soil, it may not be stick together to the hands. Then second one is your moist soil. It is having friable consistency. Friable means easily breakable. Soil tends to be somewhat sticky when compared to dry soil. It may stick to your hands, and it is also very soft as compared to your dry soil. Your dry soil will be hard, and wet soil, it is plastic. We can see this. What is this plastic? Soils can be molded without losing its co-currents. Plasticity means soils can be reshaped to any. We can reshape the soil. Suppose if you are taking clay particle, you can modify its shape. That denotes its plasticity. Plasticity means we can regain or remodify its shape, and also we can again get that to its original shape. It can be reverted to its original shape again. That denotes your plastic consistency. So moist soil, it is friable. That means it can be easily breakable. Wet soil, it is plastic. It can be regained or remolded, or it can be reverted to its original shape. And then very wet or saturated soil. Here the soil will tend to flow as a liquid. That means the soil is having more water, so it tend to flow as a liquid. It may be due to the flow under. It may be the why it is flowing means it is due to the pressure or mainly due to the gravity. Sometimes it strongly adverse or to the object. So dry, moist, wet, or very wet. So these are different forms of soil consistency. So there is a scientist called Atterbugs. He coined some of the terminologies to differentiate the plasticity and as well as liquidity. So he studied the plasticity mainly depending on the moisture that is present on the soil, and how it is varying, and it is the ability of the soil to change, as I mentioned, the plasticities. So he coined four terminologies. First one is a shrinkage limit, or otherwise they are calling it as lower plastic limit. The soil moisture content below which the soil becomes friable. At the shrinkage limit, the moisture in the soil is very low. That means the soil can be easily breakable. If we take a soil and if you are breaking it, it is easily breakable. That is friable. And then next one is your plastic limit. That the moisture content which the soil cannot be deformed without cracking. Here we need to exert some force so that the soil can be broken. So at that limit, we can call it as plastic. And what is this liquid limit? And it is a moisture content at which the soil will loses its plasticity and become liquid. That means it tend to flow like a liquid, as we already seen in the liquid consistency. And what is this plasticity number? It is nothing but the difference between the moisture content of upper plastic limit and lower plastic limit. They are giving it as a plasticity number. Here you can clearly understand this is the solid particle. It can be easily breakable. If you are putting down the soil particle, it can be easily breakable. That means the soil is under friable limit. Then it is called as a shrinkage limit or lower plastic limit. And then plastic limit. Here you can see some cracks here. That is the major difference between the plastic limit or your semi-solid limit. In semi-solid limit, if you are breaking the solid particle soil, there will be some cracks you can see. And here, if you are breaking the soil particles, there will be no cracks. You can see here, there will be no visible cracks. That is the difference between your semi-solid and plastic limit. And in the case of your liquid limit, the soil will be tend to flow as a liquid. There will be no breaking or there will be no friable consistency. Here the soil will be tend to flow as a liquid. So whenever the soil is tend to flow as a liquid, we are calling it as liquid limit or upper limit, upper plastic limit. So these are the three terminologies: shrinkage limit, plastic limit, liquid limit. Then factors affecting Atterbugs constant. What are the factors that will tend to affect or modify this? First one is your clay content. Higher clay content increases the moisture content of the different plastic limit, and also it also tend to increase your plasticity index. Higher clay content requires more water to exhibit plasticity because of higher surface area. So presence of clay will change your plasticity. Then the nature of clay minerals. Your quartz and feldspar. Suppose we are having primary minerals, the soil will tend to be non-plastic. These quartz and feldspar are your primary minerals. Suppose we are having some secondary clay minerals, the soil will tend to be more plastic. So that is the case. The nature of exchangeable cations. Suppose if we are having sodium in our exchange complex, the soil will tend to have lower plastic limit. Suppose we are having some calcium, magnesium, and potassium, the soil will have some higher plastic limits. And also your organic matter. This organic matter also increases your surface area, thereby it tend to favor your plasticity. So that's all about today's class. If you have doubt, you can ask now.
There is only one student, Wasim.
Really?
Do you have any doubt?
Yeah,
Okay, Mahesh. That one student also is gone. அவன் போயிடுச்சு அவ்வளவுதான் கிளாஸ் முடிஞ்சிச்சு
okay, sir.